In this last video, we're going to use one more application of Hess's law to find the enthalpy of a reaction, but using a kind of different type of enthalpy, and again using the kind of the pretend nature of Hess's law, where we're going to be using the energy involved in bond forming and bond breaking. And the key concept is that energy is required to break bonds. All right, breaking bonds requires energy. I just said that. Or we can look at it as absorbs energy. And if something absorbs energy, what kind of process is that? That's endothermic. Forming bonds releases energy. That's an exothermic process. And the way we use Hess's law is, again, here's this word. We're going to pretend that you are breaking and forming all the bonds in a reaction. In reality, this isn't true. We don't break every single bond apart, and we don't form every single bond, usually only a certain number of them. Now, one thing I do want to highlight is that you have to be able to draw accurate Lewis structures. So maybe you want to go back and review that because this deals with bonds, and we have to be able to count bonds to see how many have been broken or formed. You have to have, in order to know where the bonds are, you got to be able to draw a good Lewis structure. So we're going to look at this reaction. We're going to take acetylene and add hydrogen to it to make this, to make ethane. And if we're going to, what I'm going to do is I'm going to draw the Lewis structures for these. So here's this Lewis structure for acetylene. And here's the Lewis structure for hydrogen. Since the balanced equation says 2H2, I'm going to put 2 there. And that's going to make ethane. So again, what I would do is maybe pause the video, go back and review Lewis structures. And now what I'm going to do is the same thing I've done before. I'm going to add up a bunch of numbers. Using, in this case, the enthalpy table I'm going to be using is what's known as bond dissociation energy. So this is a small subset of a much larger table, but I want to emphasize something very important. So this is bond dissociation energy or enthalpy. You can use those terms interchangeably. And this is the energy required to break the bond. The energy required to form the same bond is the same value, but opposite sign. So to break a carbon-hydrogen bond requires 415 kilojoules of energy. To form a carbon-hydrogen bond, it would release, it would release negative 415 kilojoules of energy. So that's the key thing to remember. Okay, so what we're going to do is I'm going to look at the reactants first. And again, I'm going to assume I'm breaking every single bond. Okay, so let's start with C2H2. What bonds am I breaking? Well, I'm breaking a carbon-carbon triple bond. So I look at my table, and that has a value of 837. And then I am breaking a carbon hydrogen bond here and a carbon hydrogen bond there. I'm breaking two of them. So when I look at my table, I have two carbon hydrogen bonds, and so that's 415. So 2 times 415. Now I'm going to go to my other reaction here, hydrogen, and I am breaking two hydrogen-hydrogen bonds. And so I go to my table, H is 436. So 2 times 436. I'm multiplying it by 2 because I'm breaking two bonds. Now, now I'm going to go to the products. Okay, now I'm forming bonds here, which means I have to change the sign of these bond dissociation enthalpies. Okay, so I'm forming a carbon-carbon bond. I look at my table, and that is 345. I'm going to subtract, or I'm going to put a negative there because I'm forming it. And then I am also forming 6 carbon hydrogen bonds. So carbon hydrogen is again 415. I'm going to multiply it by 6 and make it negative. Put the negative on the inside here. And just like all the other Hess's laws examples, I'm going to add up all of these numbers. So 837 plus 2 times 415 plus 2 times 436 plus a negative 345 plus a negative 6 times 415. And that releases 296 kilojoules of energy. Again, keeping track of the sign. If the sign is negative, what kind of process is this? This is an exothermic process. Now, before I move on, or before I conclude, I want to kind of dissuade you from looking at some trends. There is, certain important trends to know, like, for example, bond strength. If you look here at carbon-carbon versus carbon-carbon double bond versus carbon-carbon triple bond, what do you notice about the energy required to break those bonds? Well, we see that a carbon-carbon single bond is um, weaker than a carbon-carbon double bond, which is weaker than a carbon-carbon triple bond. So triple bonds are stronger in energy, or require more energy, I should say, are stronger bonds. But I want you to look at this. Is a triple bond exactly 3 times the amount of energy as a single bond for carbon-carbon? No, if I multiply this by 3, it's not going to equal 837. And so I just wanted to end on emphasizing that even though there is a trend between single, double, and triple, you can't just say, well, a triple bond is 3 times stronger than a single bond, or a double bond is twice as strong as a single bond, because we can see the numbers don't add up, and the numbers don't confirm that statement. We only know that a triple bond is stronger than a double bond, which is stronger than a single bond. In order to know why, that's going to require a lot of complex quantum mechanics that is way outside the scope of this course. So you don't need to know why. I just want you to know the trends as well as what trends not to hold on to.